The second non-ideality that we will deal is the non-ideality caused by thermal instability. Or these are all the part. Okay, the next non-ideality we will deal is by what is called as junction breakdown. There are different ways in which a junction breaks down in a PN junction, right? Or the current exponentially or current increases radically and it deviates from the ideal diode characteristics. The first way it can happen is what is called as thermal instability. Second one is called tunneling, and third one is avalanche multiplication. We will see each one of these things in series, and then we'll have a little bit detailed discussion on the avalanche multiplication. The thermal instability, most of these things appear under reverse bias conditions, right? Whereas the high injection that we saw before is predominantly a forward bias phenomenon. The thermal instability is easier to understand. The total current, as we saw before, is basically J naught e power QV by KT minus 1, right? And under reverse bias, basically this is much smaller than the constant term. So basically J equal to J naught under most conditions, and J naught we know to be given by this equation. Q root dP by tau p Ni square by Nd plus Q root. So we see that the actual current is strongly dependent on the intrinsic carrier density and the square of intrinsic carrier density, right? And we know the intrinsic carrier density is given by Nc Nv e power minus Eg by Kt. So intrinsic carrier density is also a very strong function of temperature, right? So suppose we have a junction which is under reverse bias, right? A large depletion width, and we have a current which flows through this junction I, right? And this I basically increases the junction temperature by the I square R losses, right? Or the product of V into I is lost to the heat in the junction, and the heat in the junction increases the temperature. And the temperature actually increases the current further because it increases Ni, right? And this kind of feeds into each other, causing you a kind of an avalanche effect which increases current drastically. So now let us plot the actual current under such conditions. So this can be done in this particular fashion. So here I am plotting the reverse bias current JR versus the potential V. It is plotted in such way that I have a voltage increasing in this fashion and current increasing in this direction, right? So I have 0.1 volts here, 1, 10, 100, 1000 and so on, and this is 0.1, 1, 10, 100 and 1000. So basically this is a log plot, and if I plot the current at different temperatures, it turns out to be straight lines, right? Because they are independent of the potential as we saw before, and the temperature determines the carrier density Ni, and Ni determines J naught, and it is directly related. The actual, let us say if this is at 20 degrees and this is at 50 degrees, and each of these currents are given by the relation I is basically about T power 3 plus gamma by 2, gamma being some constant, e power minus Eg by Kt, right? This is Ni square as we previously saw, right? And Ni and current directly depends on Ni square, so the relationship is almost cubic in temperature, right? Now with this given, you also have I square R losses giving you a particular temperature, right? So the constant power lines at each given temperature, if given, can also be drawn and which under this log plot appears to be these straight lines, and let us say this being 20 degrees all the way to 50 degrees. So you can see that the system will occupy the lines which are intersection of these two, right? So basically these are the lines, these are the points where the temperature matches with the power loss. So these are constant power lines giving you these temperatures, and the horizontal ones are the current at those particular temperatures. So basically these points are the operating points of the PN junction diode, and you can see that after a certain voltage called the turnover voltage, this is VU, the diode actually experiences what is called as negative differential resistance. Which means, so basically R is equal to, let us say, dV by di is negative after V bias is greater than VU, VU being the turnover voltage. It turns out to be negative because if the temperature is beyond the temperature determined by the turnover voltage, you can see that the current automatically increases because of the feedback effect that we spoke about. Right? And hence, for increasing the current beyond this particular value, let us take it to be 100 here, right? If the current increases beyond this value, the actual potential required to sustain this particular current is even smaller than the previous case, because the I square R losses helps to increase the intrinsic carrier concentration, leading you to have a lower actual series resistance and hence a lower bias potential which is required to sustain the current. Right? This is what is called as a differential negative resistance, which can be observed in PN junction diode under reverse bias, and this is due to thermal instability. Right? Now let us discuss the other non-ideal characteristics, which is called as the tunneling current. Right. Now this is once again a phenomena which is observed when you are under reverse bias. Right. Now let us once again consider a PN junction diode under reverse bias. Let us take, I have an EFN, right, and this being EC, right. I have an N-type semiconductor here, and I have a P-type semiconductor which is biased such that I have the Fermi level here, right? And I join these two. Now you can see that if the Fermi level is so close to the conduction band, I can have lot of electrons close to the conduction band, right? And the Fermi level close to the valence band on the P side gives you a lot of holes here, giving you a probability of an electron to tunnel from here to here, right? Now this can be dealt quantum mechanically, because there exists a huge potential. Now the electron cannot rise up this potential hill to go to the conduction band, but it is easier for the electron to tunnel across this barrier, and the tunneling probability depends upon the width of the barrier, right? And you can see that the barrier is basically a triangular one. So the tunneling probability, which can be calculated quantum mechanically for having a triangular barrier, is given by the expression T is basically e power minus 2 integral 0 to width of the barrier W K being the wave vector at each of this x here. So basically this is x direction, and W being the entire width of the barrier, right? And you can see that this being the conduction band, and it has a function of EC of x, which seems linear, right? And you know that the band structure that we draw is basically a potential profile, right? And this EC is basically QEX, and E being the electric field that is applied, right? Because you know that E is equal to dV by dx, and the actual potential is basically a product of E into X, right? So basically E being the electric field, and this V, the potential, is basically written as EC. EC is the conduction band, right? So with these things given, the actual K being the solution of the electron wave function, which we know from the Schrodinger equation can be written as minus h bar square del square by 2m plus the potential. The potential is basically the conduction band triangle that we're talking about, right? So basically it is EC of x, psi being the wave function, is equal to this E, the energy of this psi of x, and this can be written as square by 2m. Psi is E minus EC of x into psi of x, right? And the solutions for this can once again be psi is some e power I kx, where k is root of 2m star by h bar square E minus EC of x. And if we are considering electrons with an offset, saying E being the edge of the conduction band, right? And you can write this EC of x as we have written here. Basically, it's a product of the charge and the electric field in the depletion width. You can write this tunneling probability Tt as e power minus 2 integral 0 to w. K is written as root 2 m star by h bar square into minus q, E being the electric field in the junction, into x, to dx. You can see that it is already imaginary, right? Because you have a negative number inside the square root, so the tunneling probability is basically imaginary, or the wave vector of the tunneling probability is basically imaginary, which tells you that the solution is not a decaying one, which e power minus a constant will be a decaying probability, whereas e power an imaginary number is going to be an oscillating function which depends upon the width w, because it is the integral of this particular width, right? Longer the width or wider the barrier, of course smaller is the tunneling probability, right? This can be solved easily, and then the tunneling probability can be found to be e power minus 4 root 2 m star Eg power 3 by 2 by 3 q h bar E. Eg came here because you can see that this height is basically the energy gap, right? And we saw this expression. So EC will end at the energy gap if x is equal to the width, right? So basically in this equation, if I substitute x is equal to w, so basically I will get q e w will be Eg. So w will be Eg by q into E, E being the applied field, and if I substitute this in this particular limit, I will get this expression, which is the tunneling probability, right? If I know the tunneling probability, the actual tunneling current can be calculated across this junction. If you know the electron tunneling from left to right, from this conduction band to the valence band, and you subtract the tunneling probability of the electron from the valence band to tunnel to the conduction band, right? So what is the probability for an electron to tunnel from the conduction band to the valence band? So let's say J, conduction band to valence band, is an integral of all possible energies, right? It has to have a Fermi function of availability of an electron in the conduction band, number of states in the conduction band. You should have an electron which is valence, which is you should have a state which is vacant in the valence band, right? And number of states in the valence band multiplied by the tunneling probability that we calculated. Right? You can do the reverse as well. Electron from the valence to the conduction band, similarly 0 to, so basically this is EV to minus infinity, right? So basically it is not EC, sorry, this is EV top of the valence band to minus infinity. It is basically all electrons here, right? So this will give us, you should have probability of filling an electron in the valence band, number of electrons in the valence band, and you should have a probability of vacancy in the conduction band, number of states in the conduction band into Ti. The total current is J C minus V, C to V minus J V to C, and which will give you integral EV to EC FC of E minus FV of E T T NC of E NV of E D. Sorry. So if everything is substituted, the total tunneling current can be calculated to be root 2 m star by 4 pi square q cube by h bar square E, the electric field in the junction, V R, the actual potential applied across the reverse or the reverse bias potential applied, divided by root EG. EG once again comes from the barrier height, right, that we previously calculated, e power minus 4 root 2 m star EG power 3 by 2 by 3 EG h bar. There are a few things that we can qualitatively understand here, right? The tunneling current depends directly on the reverse bias potential, which is easily understandable, right? The more the bias potential that you apply, the narrower the barrier becomes. You can easily see this from the direction. Let us say that now I have a much stronger reverse bias potential, right? So now you can see that the bending in the band is now much more severe. Now this leads to the width being much smaller, but then having a much higher triangle, right? So the tunneling probability is dependent much on the width, and hence you will have a much higher tunneling current at higher reverse bias. It also depends on the electric field E. The electric field depends upon the width of the depletion layer, right? And smaller the depletion layer, larger the electric field, and hence you can see that under heavily doped PN junctions where the depletion width is much small, you will have a much higher tunneling current, right? So one, JT is larger for higher VR, that is a reverse bias, which is easily understandable. 2, when the junction is heavily doped, the width, the depletion with W is small, right? If W is small, basically what happens is it is the field, right? So we previously saw the relationship between width and the electric field E, right? For smaller E, for smaller width, electric field is much larger, right? So basically if W is small, E is much larger, and hence it will give you a higher tunneling current, right? And it is also inversely proportional to the band gap. You can see it coming in e power minus and Eg power 3 by 2, right? So the band gap JT is smaller for large band gap materials. Which is obvious, right? The wider the band gap, the taller and the wider uh, the uh, the electron acid tunnel for having a larger tunneling current, right? So basically, you will have much stronger tunneling current in small band gap materials like germanium, and then weaker tunneling currents in silicon and gallium nitride, and so on and so forth. Right? So with this treatment on the tunneling current, we will stop now, and the next time we meet we will talk about avalanche multiplication.